Ladies and gentlemen, welcome back to your cybersecurity series. My name is Vlad and I'm here to help you and support you in your cybersecurity journey, even if perhaps you don't have a technical background. Today it's episode 27 and we are continuing our journey on cryptography. And as I told you, we are really focusing on modern crypto. So things that maybe you are even using, algorithms that you might be using on a daily basis, without even realizing it. And that's one example I want to start with today. It's when you create those zip archives, so those compressed file formats. Basically, you do that with WinZip, WinRAR, or sometimes built-in functionalities within Windows or Linux. And basically, if you have been a bit curious and if you looked at some of the parameters, when encrypting a file or a folder, sometimes you are proposed with different options. And as you can see here on the right side, there will be different algorithms, so different encryption algorithms for you to choose out of. Here I'm highlighting AES. There are two different versions, one with 128 bits and the other one with 256. We will come back to that later on. So as you can see, those are the default parameters, and these AES algorithms is something that is widespread today, and you would find it in any encryption software. But to understand that, we need to wrap up and go back a bit in time, back to the previous episode where we talked about the XOR function. So if you remember, that's what we covered last time. When we have a plain text message, so here I took a series of 42 characters. So that's all the characters here capitalized, counting also the blank spaces and the exclamation point. So my plain text will be, I wish everyone knew about cybersecurity. And the encryption key has to be the same size. So here I'm also using capitalized letters. This is just an example of key to XOR with. And what we've discussed is that first we transpose those ASCII characters into bits because the XOR function only applies bit to bit. You will notice that the first 8 characters that I'm highlighting here in red actually corresponds to the first character of my message, so the capitalized I. From that, of course, we will apply the XOR function bit by bit. So I take the first bit of the plaintext, I take the first bit of the encryption key, I XOR them both, and then I move to the next character. When we do that, we get the ciphertext. And if we move that back or transpose that back into ASCII or printable characters, this is the type of output we get. So if you count them properly, you will see that there are 42 characters, counting the blank spaces and counting the carriage return, so when the text goes back to the next line. And you see those, let's say, rectangles, white rectangles. It basically shows that some of the characters were not recognized by my browser or by the PowerPoint. Basically, those characters, sometimes they are shown differently. You can have a blank rectangle. You can have sometimes an exclamation point into a black diamond. Basically, it's your browser or your text software showing you that those characters are not recognized. Because sometimes when we XOR two characters, we end up on things that are not really printable, but rather part of the metadata or the configuration of the layout. Anyway, as we've seen, of course, those elements I am not calculating myself. I do not XOR things manually. There are many websites that are available to you. One of them is decode.fr. So this website allows you to play with different algorithms, the Caesar, the Visionaire, even the XOR function that we see here. Basically, you can put your plain text as an input. You are also specifying what type of key you are using. Here, I choose ASCII key, so a plain text key, but you could choose hexadecimal, binary if you like zeros and ones, and it will display the output. You can also use this website to decrypt certain elements, and it will also propose you some brute force attempts sometimes when you don't know the key. For example, in the context of the Caesar cipher that we have discussed in the previous courses, basically it will show the 26 different possibilities when rotating the different characters. But having said that, you understand that that's the problem with what we call stream ciphers, because the key has to be the same length as the plaintext message. And this is something that is completely not scalable, because to encrypt larger data, like a file, a repository, or even a full disk or full partition, we would require a second partition on the side, and that partition would be the encryption key. So we would lose a lot of space, meaning that there has been a different strategy that was proposed, and it's called block ciphers. The idea is the same. We have a plain text shown here in green at the top, and we are going to slice that plain text into regular portions. So here, of course, if we imagine a certain number of bits, maybe it's sections of 64, 128, or 256 bits. Those numbers are not random. They correspond to the size of the keys. So here we slice our plain text in three. And on each of the portions, we are going to apply our block cipher. So the block cipher, you need to understand, is the algorithm that you will choose to encrypt that tiny portion of the plain text. So by default, you can consider that we will apply a XOR function in between the text in green, so the plain text, and our encryption key. And we do that on separate occasions. So we do that 3 times, and then we get as an output the ciphertext in yellow after concatenating back our individual portions. Maybe you are already feeling it, but there is a problem with that method. That method is called electronic codebook, so ECB. Basically, the idea is that if you have the same characters in the plain text on different portions, so if basically you have a certain pattern that repeats itself, you will get exactly the same pattern in the ciphertext, because what you are doing is always applying the same key. So XOR is a deterministic function. So if you give a certain input and you always XOR with the same key, you will get the same output. So there have been other variants. One of them is called CBC, so cipher block chaining. The idea, as opposed to the first one, is that we are going to use the output of our first portion, our first part of the text that was sliced, and we are going to feed that into the second part of the plain text. So as you see here, we have our plain text number one in green. We have also an initialization vector. It's absolutely essential in orange. We are going to do a first XOR operation in between both, and then we are going to apply the block cipher. Again, this block cipher can be just a XOR operation, can be something a bit more complex, and I have examples of that right afterwards. Then we get our ciphertext one, so that's the part in yellow, and you see that the results of that, basically this ciphertext one is going to be used as the next initialization vector for our plain text number two. So then, and we continue, meaning that all our ciphertext are chained. And maybe it's something that is not really practical for you to see visually, but I have some example with an image. Basically, if we take the Linux logo, so the penguin, we have a clear picture. If we apply first the ECB cipher, you will recognize that every time that there are a series of black pixels or white pixels, they are more or less encrypted in the same way. So meaning that we see the patterns, and everything that is white also in the picture or transparent has been encrypted as well in the same context. Meaning that in the encrypted version, we do recognize some of the content or at least some of the patterns. But if you apply the CBC cipher, then you will see that everything is scrapped. There is no way to understand certain patterns. So if something repeats in the plain text, it's not going to repeat in the ciphertext. Which is why today the modern algorithms that we are going to see, and AES, as I told you with my WinZip example, it's one of them, they are all using this CBC method. Speaking of algorithms, so as I showed you a bit earlier, this block cipher blue rectangle can be anything. And of course, that's where the complexity lies. There have been many algorithms that were invented. It's not only about using the XOR operation, even if that would be straightforward. As I told you, there have been some problems, some issues with this XOR algorithm. The idea is that if you use the same padding, the same mask more than once, sometimes you might leak some information. With CBC, it's a different kind of problem. The problem comes from the initialization vector. You need to understand that when people were implementing the CBC, sometimes they were, as part of the documentation, showing, okay, that would be an example of initialization vector. But when the people deployed those software, they were using this initialization vector example as a real initialization vector in production, which led, of course, to many people using the same initialization vector, and that ended up being kind of breakable, or at least leaking some information. Anyway, not jumping into the details there, the idea is that what lies behind this blue box block cipher box can be much more complex than just XOR operation. Just to give you an example, we have the DES. So DES stands for Data Encryption Standard. So despite the name standard, this one is deprecated. It was broken in 1997. It used to be the standard. It was even approved by the NIST. The NIST is a international organization for standardization specialized in IT technologies and cybersecurity as well. At the time, and that's what you see here, my illustration really represents what's happening in one of those blue block cipher boxes. So first, you would take a clear message, 64 bits. You would swap some characters. If you remember what we did with the matrices back when we talked about the Scitali and the Greeks, basically we are swapping characters and we are, let's say, dividing our message in two. We have a left part, we have a right part, and we are switching them every time and applying a certain function. I will come back to that in a minute. The idea is that we have a key on the right side. The key was at the time 56 bits, which is really small. And from those 56 bits, we were deducing many keys of 48 bits. So basically, you are taking a 56 bit and you are creating sub keys. That's the principle. Anyway, I will focus more on the detail, but basically in 1997, it took 3 weeks to break. A year afterwards, that time was reduced to 56 hours, and nowadays it's a matter of minutes or even seconds, depending on the calculation power of your modern device. Which is why DES we are not using anymore, but I just wanted to show you what it looks like in practice. So it's not just XOR operation, it is something a bit more complex. So just back to my schema here, there are 16 different rounds. So for 16 times, we are swapping left and right and applying this cryptographic function represented here by the letter F. And within one of those loops, so it's done 16 times in a row, one round of DES actually consists of taking the left part of 32 bits, taking the right part of 32 bits as well, and applying different methods. If you want to dive in further, I really recommend going on this Hyper website. They have a video explaining in depth how the DES is calculated. But basically, just to do it short, the right part is going to be put as the left part on the next iteration. But the right part is also being used and first expanded. So we are going from 32 bits expanded into 48 bits by adding some noise and some let's say, fake bits. 48 is not chosen at random. It really corresponds to the size of our encryption key. I told you that we went from 56 bits keys into 48 bits sub keys because there are many of them. There are 16 of them, one per round. So we are XORing our 48 right part that was expanded with this first sub key. Then we do some substitution. We compress it back into 32 bits, and then we XOR with the left part, and that becomes the right part. So you can see it's not straightforward. It's quite messy, but the idea is that you do that 16 times and you get a DES message. And despite the appearances, it can be broken quite easily. Also, last note on the algorithm, it is a symmetric algorithm, meaning that if at the top of the function you put your clear text message, you will get a ciphertext. But if you feed a ciphertext, you will get at the bottom a plain text. So it's the same algorithm which allows you to encrypt and decrypt. It's the same key, which is why we call it symmetrical encryption. And again, it might not be straightforward to understand that you will get back the plain text, but you will have to trust me on this or do your own research and dive further into the DES algorithm. Today, I told you that the modern standard is AES. It stands for Advanced Encryption Standard. It's kind of the same spirit as DES, meaning that instead of having 16 iterations, here it's called rounds, but it's the same principle. We are going to apply 10 rounds of encryption, and it's done with a much larger key, and that's basically essential because in the DES, there was only 56 bits of, let's say, randomness, which was cut down into 48 bits when generating the subkeys. Here we start with a much larger size of keys, 120 bits or even 256, which is the one recommended as of today. So this algorithm really succeeded to all of the DES variants. You can imagine that there were more than 2 algorithms. There were many spin-offs of the DES. It's compliant by the NIST standard, with the NIST standard, sorry, and it's largely used today. As I told you, it's embedded with any encryption or zip software. And it's something that is completely symmetrical. So if you put the plain text as an entry, you get the ciphertext at the bottom. If you put the ciphertext on top, you retrieve back the same plain text with the same key. The idea is similar to DES. So as you can see here on the graph, first we have an initial key that's 128 bits long, and we are going to expand the key a bit to then generate 10 different subkeys. So just like in DES where we had a 56 key, or let's say major key or main key, then we generated 16 subkeys. Here we apply the same method. But instead of just doing left and right and XORing in the middle, here in AES, it really relies on matrices. So just like what we saw with the Romans, the Romans and the Greeks, we are putting our plain text in a grid, and then we are doing a lot of operations. So we are shifting rows, mixing columns. Basically, the matrix is going all around, and then we are applying that 10 different rounds in a row, and we get our ciphertext. So I'm just showing you that it's sometimes much more complex than just what was depicted here. It's not only XOR operation. It's about putting messages into matrices and making some complex iterations, not only once, but 10 times for AES, 16 times for DES. It's not the number of runs that so much increases the algorithm, it's more the key size. And that's also something you need to remember. It really goes back to the Kirchhoff's principles that we discussed in the previous video. The secret is not on the algorithm itself. So it doesn't matter if you do complex matrices operations. What really matters is the strength, so the size of your encryption key. And again, I really want to emphasize that today, this notion of block cipher, it's really inheriting from the previous videos that we have seen. If you remember my example and my video on Caesar and Vigenère, in Caesar we had a plain text and we were swapping all the characters by the same increment. And Vigenère introduced this idea of taking a smaller key but sliding the key, or let's say slicing our message and applying the key every time. And that's exactly the same principles with ECB. With ECB and CBC, we slice our plaintext message and we apply a key every time with a specific algorithm. Can be DES, which is deprecated, can be AES, which is the way forward today. Which is why I really emphasize on that, because it really leverages all the previous video that we've seen. And if it's unclear to you, don't hesitate to raise a question or go back to the previous videos to make it, I hope, more stable or more understandable. So anyway, that's the end of today's video. Yes, and last note on AES, it is robust for now. Many people are talking about quantum computing. That's also it's half fantasy, half reality today, let's say. So of course, this standard of using AES with encryption keys of 250 bits, it really stands today as of 2025. Some people claim that it was broken on really, really tiny example with really specific conditions. So it's not yet widespread. Of course, it will evolve. Cryptography has been evolving since many centuries now. So perhaps this will be deprecated as well, but they will come, and it's an active field of research. There will be quantum robust encryption algorithms, but it's not really widespread today, as I said. So that's it. Now I hope you understand where those encryption algorithms come from when you are using them with WinZip or any other encryption software. I hope you enjoyed, and see you soon in the next video.